All right. Hello, guys. Hope all of you are well. So today we're starting with these MCQ madness sessions. So basically, some of the papers that are still left, we are going to be doing the hardest questions that we can do out of all of these from some of the most recent papers. So that's going to give you a really good idea of how well prepped you are for the exams. So in the past, we've been doing entire yearly papers. So right now, we're just looking at these topical questions, not topical, but from the yearly, we'll be looking at the most difficult questions that we can possibly get our hands on. Let's start. All right. So this is summer 23 paper 1-2. It's one of the homework papers. So I guess question number 1 is pretty easy, 2 is easy, 3 is easy. And also we've done some of these in class as well, because in variants you do tend to have questions being repeated. Let's have a look at this one. The curved line on the distance time graph shows the motion of a toy car. The straight line is the tangent to the curve at 10 seconds. What is the speed of the car at 10 seconds? Again, without even looking at the graph here, you first identify what type of graph you have, which in this case is a distance time graph. So the first step you've done, which is to identify that this is a distance time graph. The next step is to say that now, if this is a distance time graph, without even talking about the type of shape we have here, we are going to recall its features. So we know that the gradient of a distance time graph is speed. This tangent here, you know that the tangent is used to find the gradient at one certain point. So the tangent is really going to give you the gradient because you have drawn the tangent. So what you just need to do now is to find out the gradient of this line. So first off, you can see that the tangent is drawn to the curve at 10 seconds. So at 10, you can see that this point is pretty neat and you can just pick what this is. So this is 10, 6, right? Time 10 and distance 6. And now I just need another point for the calculation of the gradient, which is going to be the speed. And for that, I'll pick out this one. Always pick such a point in which the coordinates are very, very clear. This is why I did not pick up a point like this, which is neither at this edge of a box, neither is it in exactly in the middle. So always pick these coordinates, which are very, very easy to see. I haven't picked this one, right? This is not very easy. Is it 0.5 or is it right at the edge of the box? You should always be mentally looking for a 0.5 or exactly at the edge of a box. Similarly, if I zoom into this graph and zoom into another part, see, this point is also not very clear, which is why I did not take it. I could have possibly taken this as well, right? So that's what I could have done. But anyway, I have 10, 6, and this one is 0, 3. So the tangent is just going to be change in y over change in x, right? y2 minus y1. So 10 minus 0, right? Over 6 minus 3. So this is 10 over 3, 3.33. So that's 3.3. All right. Let's have a look at another one. All right, this is also a good question. The diagram shows 4 balances, W, X, Y, and Z. Scales of all balances are calibrated on the Earth to measure mass, right? So all of these are designed for use on Earth to measure mass. Which balances also measure mass correctly when used on the moon? All right. So this is something which hadn't been assessed for a long time, but if you remember, we did discuss this in a lot of depth when we were studying mass weight density. So the idea is that the spring balance would not give you the same correct mass when it's used on the moon because it works on the basis of the extension of the spring. And because small g is different, the weight is going to be different. And hence the extension is also going to be different here, right? I'm talking about this equation. If f is going to change, then obviously x is also going to change. This will not give us the same read. So any option that contains w is out. So it's not this, it's not this. A top pan balance also uses sensors which are designed according to Earth. So this top pan balance is also not going to give us the correct reading when on the moon. And then the lever arm balance or the two pan balance, which we call a beam balance, this will work perfectly fine because this works on the idea of comparing masses, comparing weights, right? If you look at these syllabus guidelines for this thing, so it says that these two pairs of these two instruments, they compare masses by comparing weights. Now, is G going to change when you go to the moon? Yes. But if I'm talking about these two masses, which were previously balanced on the Earth, right? So I can now say that if I talk about their masses, then small g can change, right? This small g can change for both of these. But the idea here is that because small g is changing for both of them, it's going to change for both of them equally. So the gravitational field strength does not have any effect on the working of these two instruments. So here it's going to be y and z, right? Because these work on the basis of comparisons. So if you think about this in terms of an equation, then small g's cancel out on both sides anyway. Let's go on to another one. This is easy, easy. Also really easy. Newton's third law describes a pair of forces which shows whether the two forces are of the same type and whether they act on the same object. So the types of forces are the same. We have talked about this. If one is friction, the other one is friction. If one is a reaction force, the other one is a reaction force as well. And they act on different objects. All right, question number 9, also somewhat easy. The stopping distance of a car is the sum of thinking and braking distances. Which factors affect the braking distance? Speed of the car is the only factor which affects both thinking and braking distances. Tiredness of the driver does not affect the braking distance. So it's either this or this. And condition of the road does affect the braking distance. So C. This is also easy. Question like this we have done in the past. All right. Question number 12, a worker pulls a rope with a force P through a distance D in the direction of the force as shown. This causes a block of weight W to move vertically upwards through a height H. How much work is done by the worker? So he's applying this force, right? So you can see that it's this force and the distance moved in the direction of this force. So it's just P. Right? Similarly, by the same reasoning, because this force which is applied causes this weight to move upwards, if the answer was WH, this would also be correct. Right? Because of this idea that work done equals energy transfer. So this W also moves through this height H, so PD or WH would be a correct answer. But for WH, the examiner would also give you something that indicates 100% efficiency, right? So no energy losses. So he would say something like this, that the pulleys are frictionless or something. So in that case, the answer could also be WH. Easy. In cells, you have a store of chemical energy. All right, let's have a look at this one. 15, in an experiment, the volume of gas in a cylinder is measured as the pressure of the gas is increased. All right, so pressure is increased, so volume is measured. So pressure is increased to 1, 2, 3, 4, and volume goes like this. So it goes 20, 10, 6, and 4. What is the possible explanation for these results? So always remember that being an inverse proportion does not mean that these would have constant, that how much this increases by would also be the amount this decreases by. That's not how inverse proportion works. Instead, for inverse proportion, you remember this idea in the context of this equation, that the product of pressure and volume is always constant. So if you do both of these times one another, this would be exactly 20. If you do both of these times one another, this is 20. You do both of these, this is 18. And then this 4 times 4 is 16. Right? So here what is happening is PV is decreasing. It's initially constant and then it decreases. All right. So what is a possible explanation for these results? So the pressure is increasing. And here what should have happened is that the volume should have decreased by, if I think about this pressure. So this volume, because this tripled, this should have become 1/3. So 1/3 of 20 is what? 1/3 of 20 is 6.67, right? So this should have been 6.67, but it's less. The volume is less. All right. After the pressure is doubled, gas starts leaking into the cylinder. After pressure is doubled, gas starts leaking out. Temperature of the gas is constant. Temperature of the gas is increasing. Now we know this cannot be the case. All right. Temperature of the gas, if this was constant, then PV should have been obeyed, right? But it's not being obeyed. So this is definitely out. All right. So then let's have a look at the other options. So the other options, just a sec. All right. So yeah, what were we talking about? So yeah, we said this, that the volume is less than what it actually should be, right? And you can also do this. If you use this, then it should have been 5 into 10 to the -5, but it's actually less here as well. So then, yeah. So then the volume is less. What could be a possible reason for the volume being less? If the gas, so obviously it should be either of these, that after the pressure is doubled, because here, as you can see, when the pressure doubles, PV stays a constant, but it's after that that it's not constant. So after that, if gas actually started leaking into the cylinder, this means there are more particles and they would take up more volume, right? Then it should have been more than this value. Should have maybe been a value like 7. But it's actually less than what it is here, which leads me to conclude that the answer is B, which is that the only reason why the volume is less than what it actually should have been is if some of the gas leaks out of the cylinder. All right. Why is D wrong? D is wrong because if the temperature of the gas is also increasing here, then if the temperature of the gas is increasing, it should have occupied more volume, not less. All right. So that's why the answer here is B. Does this make sense? If the temperature should have increased for D, in part D, if the temperature increased, then because of this idea that when temperature increases, volume increases, it should have been more. This is a pretty tricky question. All right, let's have a look at this one. A ray of light passes into a block of transparent material is shown. What is the refractive index of the transparent material? So first of all, the thing you guys should all identify is that none of these angles are marked with respect to the normal, which is what you need here to calculate the refractive index. So this is our normal. So if this is 35, then this remaining angle, this one right here, which is 55, would be this angle, and also this angle would be 30. And then you use the refractive index formula, which is sine of angle in air over sine of the angle in the other medium. So the angle in air is 55. So it's sine 55 over sine 30. Right, so sine 55 over sine 30. This would be C, 1.64. 21 also really easy. D, oh sorry, not D, it's C, because this is the critical angle, the angle of incidence, which causes the angle of refraction to be 90. Right? Always do make sure that you know what angles these are. For example, if you remember in your paper twos, you were asked this question when this, actually it was a question which was more like this, and you were asked what is the angle of incidence here. The correct answer is that the angle of incidence is 0 degrees here, because if this is the normal, it makes no angle. It's pretty similarly in the case of refraction, this is the angle that you're going for, which is 90. All right, let's also have a look at 22. Which radioactive isotope can be used for measuring cracks or flaws in metal components? Okay. So in metal components, we know that it must have a certain degree of, it must be very penetrating, right? So that it can actually go through the metal. So we definitely don't need alpha here, because alpha is not very penetrating at all, right? So it must be gamma. And then if we look at the half-life must also be pretty, it should be at least somewhat long. It should have a long half-life, so that we can, for example, if we're having this radiation being incident on some metal, so we can also get it back pretty easily, right? So it should also have a good half-life. Hence it's all right. What else? 24, what proves that a metal bar is a permanent magnet? So permanent magnet, the test for this is repulsion, right? Uh, because because temporary magnets are always going to attract, but a permanent magnet is going to repel. I guess we have done this, but still, what is the advantage of using 3 cells in parallel rather than a single cell? Is because it lasts longer, takes longer to discharge. This is also not very difficult. Max resistance is all of these in series, so 3 times 15, which is 45. And the min resistance is all of these in parallel, which would be 15 over 3, which would be 5. So that's this. All right, let's have a look at 30. Resistance of R increases. What happens to the 2 voltmeter readings V1 and V2? So if resistance of R goes up, then the resistance of this entire parallel combination also goes up. And because of that, the voltage across this would increase. So V2 has to increase. And by a consequence of voltage division, because V1 plus V2 always equals this. So if this goes up, this has to go down. So V1 should then decrease. Should be really easy to you now. 32, a coil of wire above a magnet is dropped. As the coil falls over a magnet, an EMF is induced across the coil. What does not affect the magnitude of the EMF induced across the coil? Changing the number of turns would affect the magnitude of EMF induced, because more turns would also mean that you have a greater EMF induced, right? More field lines would be cut by the coil. Changing the height would again affect the velocity, and that would affect how fast it cuts those turns. Changing the direction of the magnet just changes the direction of the induced EMF. Changing the strength of the magnetic field would also affect the magnitude of EMF. The results of alpha scattering give evidence for the size of the nucleus, right? For some reason, these types of questions are a bit difficult to students. Let's have a look at this. A sample of isotope with very long half-life is placed next to a detector. Sheets of different materials are inserted one at a time between the radioactive sample and the detector. Background rate is subtracted from the readings on the detector, and then the corrected count rates are recorded. Which type of radiations are emitted by the sample? So we have no sheet inserted versus a thin aluminum sheet. So this blocks out some of the beta. So there is definitely beta here. And then with a thin lead sheet, uh, if it's a thin lead sheet, this means that gamma also goes through. And with a thin paper sheet, the count rate is pretty much the same, right? For this increase, we can basically attribute it to the randomness of radioactive decay. So it's not alpha, it's beta and gamma. So that's C, right? This decrease shows beta and this decrease shows gamma. All right, for T, so you have to predict the correct order of stages. 4 of the stages in the life cycle of a star until it becomes a red giant is shown. Inward force is balanced by an outward force. So we know this has to do with the stable life cycle of a star. Internal gravitational collapse produces an increase in temperature. So the inverse gravitational collapse we know is a later stage. It's definitely after this. And it expands, and most of the hydrogen has been converted to helium. So for it to become a red giant, obviously it needs to expand at some point, right? So we know that it would expand, and then because of the increase in temperature, a lot of the hydrogen would be used up very quickly. So it's definite that we have this order of events that you obviously need to have X first, right? So starting from the earliest one, just a sec. Yeah. So the All right, just a second. It's until it becomes a red giant, inward force is balanced by an outward force from the center. All right. Oh, so this is until it becomes a red giant. All right. I thought it's maybe after this stage. So it basically has to do with the stable life cycle of a star. All right. So yeah, this is so X is definitely the first one. Internal gravitational collapse produces an increase in temperature, right? And then because of the increase in temperature, you now also have a increase in temperature which produces an outward force. So the inward force is then balanced by the outward force. And then because of the outward force, so it's now in the stable life cycle of a star. And then as it basically goes towards that red giant stage, the hydrogen has been converted to helium. And when that helium also fuses together, it releases a large amount of energy, which causes it to expand. So it's like X, W, and then Z, and then Y. right? So it's D. All right, so that's this paper. Let's go on to another one. Winter 23, paper 1-2. Question number 2, the graph. This is what this is. All right, so the car is traveling along a straight road up a hill. Which quantity for the car is constant and greater than zero? So here you can see that because the distance time graph is basically an upward sloping line, this means that it has a positive gradient and hence it does have some positive constant speed. So I don't see speed here. Acceleration is zero because speed is constant, right? Displacement is greater than zero, right? But it's also not going to be constant, which is why displacement is out. GPE, if it's traveling at constant speed up a hill, so what quantity is constant and greater than zero? So if it's going up a hill, it's constantly going up some height, right? It's constantly going up some height at a constant rate. So it's definitely not constant. So it must be kinetic energy, which is pretty obvious by that formula half mv squared, right? Because speed is constant, kinetic energy is also constant. All right, let's do 5. A small submarine of mass 1000 kg sinks in water with a constant speed of 2 meters per second. What is the resulting force exerted on the submarine as it sinks? So it's sinking at 2 meters per second, right? If it's sinking at constant speed, what does this mean? Constant speed means resultant force is zero because acceleration is zero. So this has to be. All right, this looks like a good question. Stopping distance of a car traveling at certain speed is measured in 4 different situations: on a dry road with new tires, on a dry road with old worn tires, wet road, new tires, wet road, old worn tires. Results are shown. So you have the stopping distance given. Now, if you look at all of these conditions, I think that the least stopping distance, which is 12, must be when you have a dry road and new tires, right? So that's definitely dry road and new tires. And then the greatest distance would be wet road, old tires. So wet, old, right? And then which two results have possible measurements on dry road with old worn tires? So there's it would be either of these, right? These are the intermediate ones. So it's X and Y. So it's definitely easier than it looks. It's what else do we have? So let's go on to 10. Which expression is equal to impulse? So impulse is delta P. So there are two equations, which is F delta T, or the other one is just calculating the change in momentum, mv minus mu. So change in momentum over time is force. Change in momentum is equal to impulse, and force times time for which the force act would be correct. So this is wrong. B is the correct. All right, 11. For some reasons, students do have trouble with energy problems in which friction is involved. Let's do one of these. A box with mass 4 kg is pulled from rest along a horizontal floor by constant force F. Constant frictional force of 1 Newton acts on the box. When the box has traveled 1 meter, its velocity is 1.5 meters per second. Kinetic energy of the box is equal to the work done on the box. What is force F? All right. A diagram would definitely help here. Let's do that. So this is the object, this is the force F, this is the frictional force 1 Newton. And then when it has traveled 1 meter, the velocity is 1.5 meters per second. So it says kinetic energy of the box is equal to the work done on the box. What is the force F? So work done, you can see, would obviously be by F, but there's also this 1 Newton force which is opposing it, right? So you can say that F minus 1, this is the resultant force which is doing work, and the formula for work is force times distance. So the distance is 1 meters equals the kinetic energy, which is half into 4 into V square, which is 1.5 squared, right? So then we just calculate this. So half times 4. So half times 4 times 1.5 squared. This is 4.5. So F minus 1 is 4.5. And then F would be 1 plus that. So this is 5. All right. So that's how you do this. Some of you guys might also be thinking this, that this would be the work done, but friction takes away energy from the system. So that would also lead to the same approach. In that case, what you would do is kinetic energy minus the work done by this would equal this frictional force times the distance. So yeah, that would also lead to the same answer. Let's have a look at 15 now. A battery delivers 3000 joules of energy to a small 2-watt electric motor before the battery stops working. For how long is the motor switched on? So all of the time units are in minutes. Do take care of this. So power equals energy over time. So time would be energy over power. So 3000 over 2, which is 1500. And by default, because all our units are SI, this is seconds. So 1500 divided by 60 is going to be this time in minutes, which turns out to be 25. All right. Let's now look at Pod X and Y are both in a cool room. Pod X contains hot water below its boiling point. Pod Y is identical to Pod X but contains water that is kept boiling by a hot plate underneath it. What happens to the average kinetic energy of the particles in liquid water in X and the average kinetic energy of particles in Y? This is really a good question. For X, what would happen? There's not a state change happening here, right? It's not boiling, unlike Y. But we know that evaporation would consistently be happening because this is a liquid, right? So the kinetic energy would definitely be decreasing. What about the kinetic energy for particles in Y? Well, because this is a state change, we know that temperature stays constant, right? So if temperature stays constant, this also means kinetic energy stays constant. So this is B. All right, make sure you have a really good grip on the ideas of internal kinetic potential energy. As far as the kinetic model of matter is concerned, there would definitely be questions which are going to assess this. Let's now have a look at so this is also easy. Which arrow shows the wavelength of a longitudinal wave? Now keep in mind that even if there was a wavelength marked here, this could have also been correct, right? Because you don't know what graph shape this is, but here both of these are not the wavelength. One of these is the amplitude. The other one, if you see properly, this is half the wavelength. This is supposed to be the full wavelength. Obviously, this is not the wavelength. These basically show distances between sort of like compressions. So this is what we're going for. This is the correct answer. '31. A student rubs different rods held in his hand, which rod gains a large electrostatic charge. Again, magnetism, and rubbing it with a magnet would not really induce a charge. So a polythene rod rubbed with a woolen duster is what we're going for, right? Because both of these are insulators. And this is also not something which is really applicable here. So the examiner really tried to confuse you here as by involving magnetism here as well. 34 is this one. So this one says two identical resistors are connected first in series, then in parallel. The two resistors in series are connected to a power supply and the current is IS. Parallel combination is connected to the same power supply and the current is IP. What is the ratio IS to IP? So IS is current in series, right? So current in series, if I just make two resistors in series, these are two resistors in series and these are the same two resistors in parallel. Now, if I think about it, if they're connected to the same power supply, so if I think about it in terms of this equation, V equals to IR, so this means V is not changing. And what this means is I and R are really inversely proportional, right? So if I need the ratio of IS to IP by inverse proportion, that's going to be the ratio RP over RS. All right, just because of the inverse proportion, right? This ratio flips. All right. So if I look here now, in this case for the series resistance, the total resistance in terms of R would be 2R. In terms of these resistors, it would now be R by 2, right? So resistance in parallel is R by 2. Resistance in series is 2R. So this would become half over 2. This would become 1 by 4. All right. It also just makes sense intuitively because you know that the current in the series resistance would be smaller than current in parallel because in series resistance is larger. So here it's going to be 8.5. All right, let's see what else do we have. This is easy. A wire is placed at right angles to a uniform field. There's a current in the wire, it experiences a force. Beams of alpha, beta, and neutrons are fired into the magnetic field in the same direction as the conventional current in the wire. Which beam experiences a force that is initially in the same direction as the force experienced by current carrying wire? So we know that the current carrying wire, when we use the Fleming's left-hand rule to figure out the direction, we take the direction of the conventional current as the direction of current. So that means the flow of positive particles. So it would be the same for alpha. It would not be the same for beta. And neutrons being neutral would experience no charge at all. So in this case, the answer was B. All right, let's do this one as well. 38 related to a CRO. The diagram shows the trace produced on the screen of an oscilloscope due to an alternating voltage input. Time base on the oscilloscope is set to 4 milliseconds per centimeter. What does the trace look like when the time base is set to 2 milliseconds per centimeter? So first things first, if the time base is changed, nothing will happen to the vertical aspect of waves. So it's two boxes first. still going to be two boxes. So it definitely can't be B or D. We know that what affects the amplitude is the Y gain. Now for this, you can just do some really simple math. You know that the time period is the time base times the horizontal divisions. If it's the same trace, so if the time base decreases, the horizontal divisions will increase. So if here it was taking 4 divisions for one wave, it's now going to take more divisions. So it's going to be C. All right. All right, let's have a look at 40. When observed on Earth, redshift of light from galaxy Y is smaller than the redshift of light from galaxy. All right, when observed on Earth, redshift from X is smaller than the redshift from Y. So if redshift is smaller, this means that it's closer and it's also moving slower, right? What we say is that the galaxies which are further away are also moving away faster. So which galaxy is closer to the Earth? X is closer. And what's moving away faster would be the one showing the greater redshift, which is what? So it's B. Let's also have a look at 39. Half-life of a radioactive isotope is 2.5 minutes. This isotope is the only radioactive isotope. Between 0 and 7.5, the mass of the isotope decreases by 70 micrograms. What is the mass of the isotope at time t equals to 0? All right. So for this, let's make a small arrow diagram as we usually do. Let's say this is the amount initially, right? Half-life is 2.5 minutes. So till 7.5 minutes, this would be 3 half-lives. So 8, then it halves A by 2, then it halves A by 4, and then it halves again to give us A by 8. It says the mass decreases by 70 micrograms. So A by 8 is what finally remains. A is what was there initially. So A minus A by 8. This is 70 micrograms. So this is 7A by 8, which is 70, right? So A would just be equal to 80 micrograms. Do focus on these words related to radioactivity questions, where it either tells you the final amount or whether it tells you by how much it decreases. Right? In this question, we were told by how much it decreases. That's why the answer was this. All right. So that's it for this session then. We did 2 papers, the most difficult questions, which I also felt and what we also saw from the examiner report. So next time out, we'll start with some of the IGCSE papers. All right. Thanks for your time, guys, and see you in the next session. Bye.